Okay. Good evening, everyone, and thanks for being here today. And my name is Xinyu Zhou, and I'm very excited to share my topic about the AutoMQ and the newest feature of AutoMQ table topic. And I will show how to use AutoMQ to bridge the gap between the streaming and analytics with Iceberg. So before that, I would like to introduce myself and. I'm the co-founder and CTO of AutoMQ, and before founding AutoMQ, I worked for Alibaba Cloud for about 7 years, and where I was responsible for some messaging and streaming products in Alibaba Cloud. And I'm very active in open source community, especially in Apache community, and I'm one of the member of Apache Foundation and the PMC member of AutoMQ and the incubator. And also I'm mentoring a new Apache project named Apache Omoro, which is a lakehouse management system for data lake. And so let's begin. Okay, today I will introduce my topic in 4 parts. First is about the AutoMQ and the evolution of the streaming world. And the second, let's deep dive into the architecture of AutoMQ and its advantages. And then I will show the new feature table topic and show how to integrate AutoMQ with Apache Iceberg and along with the AWS latest product, AWS S3 tables, and which was launched at this year's reunion. And finally, I will show a demo to demonstrate how to use AutoMQ and along with the AWS S3 tables and Iceberg. Yeah. So let's go to the first part. Basically, AutoMQ is a new project and it's a cloud native alternative to Apache Kafka. And we have replaced the Intel storage layer of Apache Kafka to cloud storage like EBS and S3. And also AutoMQ is a source available project, and you can clone it and start on GitHub. And currently we have nearly 4,000 stargazers worldwide and over 40 core contributors from different companies like AutoMQ, Zhihu, Zhidoload, Jingdong, and so on. So welcome to join us, and any contributions are welcome. Okay, let's back to have a look at the evolution of the streaming world, which is evolved more than 10 years. Yeah, okay, Apache Kafka is beginning since 2011, and it has been open sourced by LinkedIn, and its excellent performance and the classic shared architecture have resolved the scalability issue in on-premise environment. And so finally, it has been adopted by a large number of companies, and it gradually became the de facto of the stream storage. So after that, the commercial opportunity started to emerge. So there are two big Kafka vendors, Confluent and Redpanda, are leading the technical innovations. The biggest technical innovations of Confluent are the K-Route and the tier storage. K-Route makes the Kafka architecture cleaner, and while the tier storage can reduce the storage costs. And Redpanda has rewritten the Apache Kafka through native language C++, and uses the Zaft replication protocol instead of the SR. So leading to further improvements in performance. But basically, both Confluent and Redpanda are based on shared nothing architecture and with tier storage optimization. So there are regards to the architecture, there are no big differences between Confluent and Redpanda. And today, cloud native technologies are reshaping the infra software in the realm of stream storage. There are two companies have emerged, like WebStream and AutoMQ. Both have successfully implemented cloud native Kafka and achieved an impressive tenfold reduction in costs. And the WebStream architecture is very clean and is built on direct and S3. And but it has two issues. The first one is the latency issue. In each write to there are more than 1 second end-to-end latency of WebStream. And another concern is about the compatibility. Yeah, Upstream have rewritten the Apache Kafka from the scratch, so it's really a challenge. And so there are many Kafka APIs are not supported by Upstream. And AutoMQ and also store the Intel data on audio storage. But we have a different architecture, and by decoupling the storage and the computation, and we offload the storage to EBS and S3, and it's a truly shared storage architecture, and also we don't have the latency and the compatible issue yet. So let's deep dive into the architecture of AutoMQ and its advantages. Yeah. The biggest innovation of AutoMQ lies in the storage layer. Yeah. And we have developed a stream storage library called S3 Stream, which combines the EBS and the S3 storage. Yeah. And there is no replication because the cloud storage also ensure the durability. EBS has multiple replicas, and the S3 has erasure code to provide more than 12 lines durability. So there is no replication. And so you may wonder that why we need two kinds of cloud storage, EBS and S3, and that's because there is no one single type of cloud storage can meet the demands of stream storage. As the stream storage requires no latency and low cost and high throughput. And although the S3 almost meets all the requirements, but it has a high latency. Yeah, it's not optimized for high IOPS scenarios. Yeah. And so EBS offers sub-millisecond latency, but its space is very expensive. So we use EBS as a wall storage and S3 as a data storage. For each block, we only need 10 GB EBS volume. The cost is negligible. So now we have S3 stream, and then we replace the Kafka storage layer with S3 stream, and we transferred the architecture of Kafka from shared NAS architecture to shared storage architecture, and eventually it became stateless. So we can deploy AutoMQ cluster just like a stateless service. Microservice is very easy, and we even can employ the support instances. Yeah. And then we can automate everything to achieve an elastic architecture. We show a matrix collector to collect the key metrics from the Intel cluster, and so now we have two automated controllers. Yeah, the first is the auto scaling controller, and it watches the loads of the Intel cluster and makes decisions to scale in or scale out the cluster in response to the workload, the load. Yeah. And we have auto balancing controller and the two which can minimize the hotspotting by dynamically reassigning partitions over the Intel cluster. So you may wonder that why AutoMQ can claim its architecture is cloud natively. And that's because we designed AutoMQ for the cloud, and we have leveraged many cloud native technologies to design AutoMQ. Like we use the durability of cloud storage, and even we use a multi-touch feature of EBS for failover, and the elasticity of APIs to provision resources like EC2, and even we can use support instances to deploy a stateful storage system. Yeah. So this is why we claim our architecture is cloud native. Yeah. Okay, you will find the core components of AutoMQ is the S3 stream. So let's explore it in more details. Yeah. And in S3 stream, data from the producer is written to wall storage persistently and then uploaded to open storage in nearly real time. Yeah. And the consumers can read data from the S3, and of course there is a memory cache for the acceleration, so the turning rate consumers no need to access the data without the object storage. Yeah. And what's more, the S3 stream consists of a shared wall storage and object storage. And the important that is that the wall storage can have many implementations, it's very flexible to compensate the differences between in the cloud storage abilities among various cloud providers. Almost all of the cloud providers offer us EBS storage, so we can use EBS as a wall storage. And some of cloud providers like Azure, GCP, and Alibaba Cloud even offer regional EBS. So we can mix it. It's a good idea to use regional EBS as a wall storage. So even if you have a high performance alternative to S3, like you deployed a MIO cluster on high performance SSD devices, or your business is latency relaxed, you even can use S3 storage as a wall storage. So that means or the architecture of AutoMQ also supported build on S3 directly, just like WebStream. So it's about the architecture of AutoMQ. And so then I would like to share the advantages of AutoMQ, and the most important one is the cost. AutoMQ can reduce the 90% of the cost of both for the storage and compute. And for storage, AutoMQ replaces three replicas EBS volume with a single replica of the storage. So which is 20x cheaper. Yeah. For compute, because AutoMQ is an elastic and serverless architecture, so it can prevent over provisioning, and even we can use support instances, so we can achieve a 90% reduction in computer costs. Yeah. And what's more, AutoMQ's shared storage architecture greatly enhances the operational efficiency. Yeah, like for partition reassignment, AutoMQ can reassign a partition in seconds. That's because there is no data replication involved, but it can take up to several hours for every Kafka. Yeah, when it comes to the cluster scaling, and AutoMQ can balance the traffic of new nodes over the entire cluster in seconds by reassigning partitions in batches. But it can take up to days for average Kafka. And the third one is about the compatibility, and AutoMQ is fully compatibility with Apache Kafka. Actually, we have replaced the storage layer of Apache Kafka, but we kept all the code from the computation layer. That means that all the features like compile topic, identifying producer, and transactional messages also are supported by AutoMQ. And in fact, we have replaced the storage layer through a very small log segment aspect. So it's easy for AutoMQ to synchronize the code from the Apache Kafka upstream. So in the future, AutoMQ can very easy can support the new feature very easily. Obviously, it's a bigger challenge for many Kafka vendors. Yeah. So this is the bigger advantages of AutoMQ. Okay, let's go to the third part. I would like to introduce the table topic and how to integrate with S3 tables and Apache Iceberg. Yeah. Before that, I want to share a vision about the data architecture. And we can observe that there is a trend that all the data-intensive software will eventually store the data on object storage. Yeah. But even though all the data is stored on object storage, but there is no simple way to share the data between different systems. The ETLs, the data formatting conversions are needed here. Yeah. So we recently from the shared storage architecture to shared data architecture is the next critical evolution of data technology. Yeah, so the table solution like Iceberg have unified the table format in data lake. So we think Iceberg can make this happen, make the shared data architecture happens. Yeah. So we have imagined that the shared data architecture of AutoMQ, and the data is the data is generated in a streaming manner and stored in block storage. So the Flink jobs, the Spark jobs, and the Kafka consumers can manage the real-time values of the data in stream APIs. But after the data loses its freshness, the table topic feature can convert the log data to the table data. So that means that all the technology of big data can access this data through a zero ETL approach. So there is no need to replicate data here between different systems. So this is why we would like to develop the table topic feature. So let's have an in-depth look at the table topic architecture. It's a built-in feature in AutoMQ. Basically, it's a new type of topic. Yeah, it's a hybrid with stream topic and the table. Yeah. So there are three parts of the table topic. The first part is about the schema and the catalog management. And we support a built-in Kafka schema registry and support automatic schema evolution. And also we currently support AWS Glue and the table bucket as a catalog service. And in the future, we will also support the rest catalog service. Yeah. And the core component of table topic is the table coordinator. Okay, each topic has a table coordinator and always run with a partition 0. And which is responsible for centralized coordination for Iceberg snapshot submissions and to reduce the commit frequency and avoid performance conflicts. And the next is the table workers. Each AutoMQ broker has an embedded table worker and with Iceberg writer, and is responsible for writing all the data from the streaming to the table. And also, all the partitions in current broker will share the same table worker to reduce the CPU and the memory usage. Yes. And the table workers will handle the data uploads by listening to the commit request events, which is emitted by the table coordinator through or inner control topic. So this is the architecture of a table topic. So let me share the benefits of the AutoMQ table topic. And firstly, it's very easy to set up. Yeah, you only need to, when you are creating a topic, you only need to single click to enable this feature, and there is no extra configurations, no Flink jobs, and no Kafka Connect. And also we support building schema registry, and AutoMQ has an out-of-the-box Kafka schema registry and support auto creation of Iceberg tables and schema evolution. Yeah. And the most important benefits is a zero ETL. We can eliminate the traditional ETL pipelines, and which can reduce the costs and the operational complexity significantly. And next is the auto scaling. And we also know that AutoMQ is a serverless architecture, elastic. Yeah, right. And so table topic is a built-in feature. So the table topic can leverage the auto scaling and auto balancing controllers to balance the load between the table workers. So it's an auto scaling feature. And finally, the AutoMQ table topic can seamlessly integrate with AWS S3 tables, the latest AWS product, and we can utilize the S3 tables high performance and integrate the catalog. And the most important is the table maintenance. So we don't need to worry about the table and the data compaction and snapshot management. The S3 tables will handle these jobs. And also, AutoMQ table topic can seamlessly integrate with the AWS analytics products such as Asana, EMR, Redshift, and QuickSight, and so on. Yeah. So let's go to the final part. And I would like to share a demo to show how to use the AutoMQ table topic. So first, you should subscribe to the AutoMQ, and AutoMQ provide run your own cloud model, also named BYOC product on the AWS marketplace. So that means you can install the entire AutoMQ cluster into your own AWS account and VPCs. So the first step is subscribing the AutoMQ and install the AutoMQ control plane into your own account. Then you will get a URL of the AutoMQ console and with an initial password. So after logging into the AutoMQ VLC console, and you can create an AutoMQ instance with table topic enabled. But before that, you should visit the AWS S3 console to create a new type bucket, a table bucket, and record its ARN and associate it with the AutoMQ instance. And then you can create a test topic and with table topic feature enabled, just one click to enable the table topic when you are creating a test topic. Yeah. So after creating a table topic, now we can prepare some data. And this demo we have select a clickstream schema which has many columns like event ID, event name, event time, event type, and then we prepare some data and send this data via Kafka Arrow console producer and send this data to the table topic. Okay, after sending the data, we can query the table data from the AWS Athena. It's very easy. So we can just use the simplest SQL to select all the data from the AWS Athena, and you will get the result in just seconds. Yeah. So this is a very simple example to show how AutoMQ and AutoMQ table topic integrate with AWS S3 tables and Apache Iceberg. So that's all about my presentation. And if you want to further communicate with me, and you can connect me on LinkedIn. And okay, thank you. Any question? Welcome.
I have a question. Yeah, one of your slides showed that you had the brokers are stateless.
Yeah.
And then you can essentially write to EBS. I was wondering what recovery looks like if brokers are writing to the EBS volume for the wall.
Yeah.
But then you need to recover. So do you trap the EBS volumes and read on to somewhere else, or how does that work?
Yeah, actually, okay, I would like to open a doc. So wait a second. Yeah. Okay, it's okay. So I need to. Hi. Okay, it's a good question, and the EBS will fail. Yeah. So when the EBS is failed, and we can use the multi-attach feature to attach there is a wall A in broker A. When the broker is failed, we can throw multi-attach to attach the wall A to another broker. And the broker B will recover all the data in the wall A and upload the data to the S3. And then we can rule that all the partitions belongs to broker A to other brokers. Yeah.
So essentially, you're attaching, it's a read-only to the broker B.
Yes, we need to fence the broker A to write the wall A. Yeah, we will use the NVLP persistence realization. Yeah, it's also a feature of the EBS. Yeah. To fence the broker A to write the data to wall A. And once the fence is successful, and the broker B can recover the data.
Thank you
for the question. Okay.
So by using pixel, versus EPS, you're always going to have a higher latency.
Yeah.
While writing, it's much more faster to write to EBS than write to S3. So even while reading, S3 is much slower than EBS, right? So it is going to be cheaper for sure, but you are going to give up both write latencies and read latencies. Especially when you have, let's say, a single producer, but 50 consumers, your read latencies are going to go up. No?
And
Your read would be slower.
read the yeah no. I mean you concern about the read performance, right?
Read performance, yes.
Okay. And actually we have a cache for acceleration. So if your consumer are turning read consumers, you are reading the whole data. So you can read the data from the memory. So there is no performance issue. And if you use a cache consumers, right, and you will pull the data from string. So when you first attach the data for big in S3, and the first fetch, now we will have about 200 millisecond latency, but I think it's okay because you are reading the code data. Yeah. So, also we have some like prefetch feature to pull data from S3.
So when you write data, you write data in memory, as well as in S3.
EBS, yeah, EBS, and
EBS is only wall. So you will flush the wall from EBS to S3.
yeah.
Okay. And will you commit to the producer when you have written the wall, or would you commit to the producer when you have written it to S3?
No, when the data is written to the EBS,
You will commit to
we come to EBS.
Okay. And while reading, even if you're reading it from S3, because you have a copy of the data in memory, you can accelerate the performance. But that depends on how much memory the broker has.
I guess you are worrying about the EBS value.
No, I'm worried. My primary question is, and maybe sorry, translation maybe. My primary point is Kafka is very fast.
Yeah,
it's with localness. Right? Kafka is very fast with localness. We can have a 10 node, 15 node Kafka with localness, and we can get a very good write throughput and a very good read throughput, even if we have a 50 consumers reading from the same topic and 50 partitions on the topics, right? But the moment you move the storage from locally attached as for EBS or cloud to S3, your cloud object store latencies will almost always reduce both the read and the write performance.
Yeah, it's a question, but actually, most of the scenarios are pulling data from the memory cache, and yeah, indeed, there are scenarios are reading the core data, but S3 has a very high throughput features, and so there is no big problem about the performance. I think. Yeah. Also, we have some white paper about the performance in our website. So if you have, you can. Yeah.
Do you support S3 for persistence?
Yeah, we also actually we support, but we don't think S3 Express is a bullish price for the storage because it's very expensive and it's a single AZ product. So if we use S3 Express, we should double write to S3 Express packets in different AZs. So it's very expensive. Okay, thanks everyone.
Okay. Can people hear me without the mic? Yeah, I'm probably gonna skip the mic because the feedback. And I have a demo later. So let me share my screen before we start. All right, there we go. Cool.
No, no, no.
Nope, not yet. Yeah. Oh, there's power. Oh. Thank you. Appreciate it. So not showing up. Oh, okay. That should be good. All right. All right, I am the last talk for today. Today I will be talking about Iceberg and Python. Let me move this away from the bottom so folks can see the bottom of the screen. Yeah, so today I'll be talking about Iceberg and Python. I think a lot of the Iceberg world is very SQL centric, very Java centric. So hopefully this will be a little bit of fresh air for everybody in the crowd. So quick introduction about me. My name is Jay. I'm CTO at Eventual. I'm actually from Singapore, but I'm now based in the US Bay Area. Way back when, and I worked at Shopback when they were a very small startup in Singapore, and that was in 2015. But yeah, now I'm based in the US Bay Area. My co-founder here, Sami, has challenged me today to speak in English. So in Singlish, sorry, I will try my best. I haven't given a talk in Singlish before, so we'll see. But yeah, so my background, I work at biotech and self-driving at a company called Freenome and at Lyft Level 5. And I've always been a data person, working kind of in an intersection of data warehousing and also machine learning and data infrastructure, right? So kind of in that weird intersection of SQL, but also if you need to do things with vectors, PyTorch, GPUs, things I've built before. I've built a lot of distributed data loading infrastructure for training. So that was before kind of AI and ML, a lot of computer vision things for self-driving. I've built a lot of data warehousing for health bio kind of data, but also large streams of video coming in from your cars and your fleets of machines. And so most recently at Eventual, we are building a distributed data engine. It's called Daft. It's completely open source. I'll share more details at the end about it. The focus of the talk today is going to be very high level about Iceberg and Python. But I think using Daft, I'm going to try to introduce a lot of these concepts so that people can see that, yeah, there's a world of Iceberg that actually extends into Python and actually extends into AI and ML. So overview of today, I'm going to talk a little bit about Iceberg overall, and then maybe ask ourselves the question, how do we use Iceberg today? And then ask ourselves the other question, which is how do Python developers want to use Iceberg? And lastly, we're going to do a live demo because what's a Python presentation without some live coding, right? So just a show of hands, who has not heard of Iceberg before today's meetup? One person, okay. Who has used Iceberg? Who uses Iceberg in their daily jobs? Okay, a few. Who are Spark users in the crowd? The same people who use Iceberg are the same people who raise their hands for Spark. Okay, beautiful. So let me start with what is Iceberg? I feel like people conflate a lot of different things about Iceberg, right? Because Iceberg is, when you think of it, it's actually a couple of different things. Number one, it's a specification. So if you go to the Iceberg website, it will fully lay out to you a description of Iceberg. It's a definition of a system for you to work with tables of data. So if you have tables, tables have rows and columns. They have each column as a type, and you want to work with them, especially in the cloud, you will use Iceberg on top of it, right? So it's a description of a system. However, the description of the system isn't very useful, right? You need the ability to interact with the system. And therefore, Iceberg is also actually a library. So you can download the Iceberg libraries, primarily the Iceberg jars, which are Java JVM libraries. We will also introduce later on the Python libraries. But primarily, Iceberg was built for the JVM ecosystem, and so they were jars, right? And then Iceberg is a table format, meaning that you can interact with Iceberg tables, and they actually abstract away under the hood for K files. And so you no longer have to work with files directly, you interact now with tables. And lastly, Iceberg is also a data catalog, meaning that you can hit the Iceberg catalog and ask it, give me table A, give me table B, give me table C, right? Write to table A, write to table B. And you can also do things like read from table A, read from table B. So Iceberg is kind of all of these things, but basically it gives you the ability to work with tables of data in the cloud. And this is kind of the dream of Iceberg, right? That like you have this underlying storage layer, Iceberg, and it's giving you tables of data. And then you can use any compute engine that you want, right? So if you want to do distributed computing, there's things like Spark, there's things like Daft, which I work on. If you want to do local computing on your single machine, I don't care about cluster. My data is small enough. I'm reading a small partition. You can use Pandas, everybody's favorite Python thingy. There's a lot of new kits on the block. DuckDB, Polars, Daft is also extremely good local performance. And then yeah, there's proprietary engines. The company that I started is called Eventual. Things like Snowflake, BigQuery, everybody supports Iceberg nowadays. You can actually use a lot of these proprietary engines as well. But that's the idea, right? That like Iceberg is down at the bottom. Everything can read it, and you can kind of pick and choose what tool you want. However, I would argue that in reality, this is more what it looks like. You have Iceberg at the bottom. You have all these Iceberg jar releases, and it mainly supports JVM compute-based engines, right? And I put a number one next to Spark because really, like everything is Spark first. S3 tables was released. The first thing that it supports, Spark, right? And I think it was especially EMR Spark. And so then, yeah, you have all these other JVM-based compute engines that have that, I guess have that bleed over effect because Spark is the number one thing. Everything is a jar. Now all the JVM-based compute engines reap those benefits and also can use all that advancement, right? And so in reality, actually, your users may not even know that they're using Iceberg. Their like primary interface to the tables is using something like Spark, right? And so they use Iceberg through a data engine, and historically that is Spark. And so, to further reinforce my point, this is the Iceberg release page. If you look at all the release stuff, what do you see? They are all jars. Jar, right? There's no mention of Python, no mention of wheel, nothing in there. It's all jars. And so I think that this is a missed opportunity. Why do I think so? Number one, Python is the language of ML and AI today. I think that's undisputed, right? Local development on data, regardless of whether you're doing ML or AI, usually happens in a local environment on a Python notebook, right? And lastly, Python and the JVM do not mix well. And so I typed this in Google today. I searched Py4j error. So Py4j is the Python Java library. And the autocomplete, the very first thing, Py4j error PySpark. It shows you how painful this development experience is, right? Python and the JVM really do not mix well. It's a horrible user experience for your users who are trying to do Pythonic things on your Iceberg tables because they are forced to go through the Python ecosystem. Sorry, the JVM ecosystem. Yeah. So welcome PyIceberg. I think just within the last 2 years or so, PyIceberg has gotten a lot of momentum. We at Daft actually have been collaborating quite heavily with the team at Tabular before the acquisition, post-acquisition as well, on making this vision of Python with Iceberg a reality. And so now, the me here, right, is I don't want Spark, yes, as a Python developer, but I want all these tools, right? DuckDB, Pandas, Polars, NumPy, PyTorch, Daft. And the way you do that is instead of consuming Iceberg through a Spark jar, you consume Iceberg through PyIceberg, which is a client library in Python But then all of these compute engines, that's primarily what the user sees. The user is interacting with a compute engine such as Daft. And so how does a Python developer, what do I want as a Python developer? Number one, I need to be able to pip install it. And I don't want to spin up a Docker container. I don't want to have to install OpenJDK. I don't want to worry about my version of my jars. Pip install, like that's it, right? Number two, I need whatever tool I use to easily integrate with NumPy, Arrow, PyTorch, Pandas. It has to just work well with everything else that's nice about Python. If not, why am I using Python in the first place? Number three, local development. I don't want to touch a cluster. I don't have to run something else in order to use your product. And then lastly, I need seamless scaling. Yes, I'm working today on my laptop, but tomorrow I'm going to run it on a cluster. Right? I am going to try to like toss it over the fence to run on production data. So I need this to effortlessly scale to terabytes and petabytes. And so that's why we're building Daft. This is my main pitch slide, I guess. Daft is number one, a batch analytical engine. We do provide a SQL interface. You can run this on Python, just literally a Python string that's a SQL string. It's a batch data processing engine, and so it's meant also for large scale transformations of data on large amounts of like petabytes worth of data. It works really well with ML and AI data transformations. If I have time later during the demo, I can show you. But what that means is that, yes, we are a Python first data frame API, but under the hood is actually written and accelerated in Rust. And so you get all the kind of SIMD and acceleration benefits of Rust, especially in the cloud with async Rust. And we also built Daft to be multimodal. For example, you can have columns of images in Daft. You can have columns of tensors in Daft. You can run models with GPUs in Daft, right? These are all things that you want to do when you're working with multimodal data, including large amounts of text. You might have a whole book in a row, right? You might have a large video in a row. That's all things that you support in Daft. And lastly, we built this to work at any scale. It works really, really well on your laptop. It works really, really well in the cloud when you need to run this at large scale. So, demo time. I'm going to be very brave today and start completely from scratch, no installations. So that's what Python's supposed to be good for, right? We'll see. We'll see if it lives up to it. Okay, let me zoom in. All right, can everybody see? Let me zoom in a little bit more. Okay, so I have nothing installed right now. How fast do y'all think it is to install Daft, Iceberg, everything? Guess. Someone hazard a guess. 3 seconds. Okay, so I'm gonna install from this requirements file. Let me show you what's in the requirements file. So it's literally just PyIceberg and then Daft and then some other utilities to like I want to use them for the demo, right? Pip install. Oh no, I'm wrong one. UV pip install. Oh, sorry. I'm gonna initialize a environment first. I don't want to dirty my laptop. So this is my environment. Source, UV pip install. That was it. Now we have Iceberg and Daft on your machine. I think that was less than a second. And now when I want to play with my stuff, I'm going to start a notebook. Now the notebook's coming up. And this is my notebook. Let me zoom in. And now we can do a lot of the same operations that you might want to do with something like Spark when you're creating a table. Right, so let's create a catalog. This is a local catalog. I don't even need a Docker container because I can actually use locally on my machine a SQLite database as my catalog. It's amazing. I'm going to create a table. All right, table's created now. I'm going to load the table in. And so now I have a Iceberg table. Let me print this table object. Ta-da! I have a table now. It's all local. It's all in this namespace DB whatever stuff, right? It's all there. Now, again, primarily your users are going to be interfacing with Iceberg through a compute engine. So let me show you Daft. So all you got to do, import Daft. Now take that very same table object we had from before, and then you can now do a read Iceberg, pass in the table object, and show. Right? It has nothing in it right now because we just created the table. Let me read this like data.csv, and I'll show you what the data.csv looks like. Here is just Jay, Sammy, and Desmond. And, country, age. I'm not actually that old. They're actually that old. And then now I'm going to write to the table, right? And so after you write to the table, it's going to tell you, hey, I added, a new file in the table, yada, yada, all nice icebergy stuff. And then, yeah, now you read from the table and bam, the data's in there, right? You can keep writing to the table like that. And then you can show more data. Yeah, more data's in there now. So it gives you this very like interactive flow in your notebook. And notice there's absolutely zero JVM dependency. I can have no JVM on my laptop and this works. And it also works with things like AWS Glue, Iceberg REST, any cloud vendors you have, Azure, AWS, Google Cloud, it all works out of the box, simple pip install. So I think that's kind of like the beauty of having a purely Python environment, right? So yeah, I'm gonna hop back to my presentation. That's really it. So if you want to try it out, like I showed you, it's very simple to get started. Just pip install it, get daft. You can pip install it together with Iceberg as well. And you can find out more about what we're working on at getdaft.io. If anybody's working on large-scale data processing, especially with Spark, and you're having a lot of pains with Spark in this new world of like machine learning, AI, and like the interesting types of data that we now work with, we would love to chat. Yeah. Thanks for tuning in. Yes, question over there.
Question about just playing with this. I really noticed that very quite similarities between using that as well as using like, for example, so I was actually using like
Yes.
That DB also.
Yes.
Very similar.
Correct.
I think in terms of the thinking as well as storing the data locally, it's quite similar to that. So like in terms of like performance wise, like how is actually Daft as a compute engine supposed to like for example like for I haven't done those all like performance and stuff like that.
Yes. So I'm gonna repeat the question for the sake of the recording.
Yeah.
Question is Daft, at least locally, feels and looks very similar to something like Polars or DuckDB.
Yeah.
So how does it compare performance-wise and also maybe feature-wise to something like Polars and DuckDB?
Yeah.
Right. Okay. So I'm gonna answer this question by saying that like today, in my biased opinion, DuckDB is the fastest and best local engine by quite a large margin today. Daft actually, I think this week, are we cutting this week? Daft this week, we will be cutting our new local engine, which is a very different mode of computing for local. And that will be a pure streaming execution engine, which gives us a lot better memory stability, and it's a lot closer to what DuckDB has, right? And so as of the end of this week, we will be about 10 to 20% slower than DuckDB on a single machine for something like TPCH. But the benefit you get with us, though, is that we are not a SQL focused engine. We are a Python focused engine. And also number two, we go distributed, right? So if you ever enter a realm where you have more data than you can process on a single machine, maybe you need GPUs, maybe you need to scan 10 terabytes of data from the cloud, that's where you want to start considering, I need to use something like Daft. And it's as simple as, I don't think I demoed this, but literally like if you need to run Daft in the cloud, all you do is you import Daft and you just, where did my import Daft go? You import Daft and then you just call like Daft context set runner array. So we rely on you running your own cluster, but then if you have array cluster running, just point Daft to the address. And now instead of executing on your machine, all the execution will happen on the cluster. Yeah. Yeah, I mean, we are purpose building Daft to be very, very AI ML focused. My advice is usually, hey, if SQL and analytics is all you need, then yeah, stick with DuckDB, stick with Spark, stick with Trino. But if you're looking to, I think, get on this new wave with us, then we think that we're building kind of the next iteration of something like Spark. Yeah.
Something I would add to that too is that, as Jay said, like DuckDB and Polars are, great local engines,
Yeah.
but they're kind of in this minimum where they assume you're running it on your laptop.
Yeah.
And so when you're running things with files on your disk, it's actually quite performant.
Yeah.
But once you use DuckDB or Polars with data in the cloud, like you would with Iceberg, it's actually quite slow. You gotta have the abstraction where you're assuming everything is local.
Yeah.
So actually for all the benchmarks that we've ran and people like Daniel Beach and a few other bloggers who have done metrics as well, it shows that Dav is like at least 2 to 3 times faster than DuckDB and Polars when it comes to like these cloud rates.
Yeah. So if you do benchmark, I would highly advise, yes, benchmark the local files with like NVMe SSD, but also definitely try benchmarking against Parquet files in S3, right? That will really show you how Daft is doing the development.
Then I was thinking if you can pull out the S5, much better things like S3, right? It was actually quite slow.
Yes.
Was actually better than backlog.
Correct.
It was actually quite slow in the result. So I haven't considered this part about that.
Yep. So specifically for that point, when you access Iceberg data through DuckDB and Polars today, I believe they are actually just using PyIceberg directly. And so they just use whatever PyIceberg has, which is an PyArrow based reader. We have our own reader, and so everything is hyper optimized. All we ask PyIceberg for is, hey, give me the path to the files, and then we just do our own thing from there. And that's why it's a lot faster. Yeah, great question. Thank you. Any other questions?